All right, we're about to tackle one of the biggest questions in all of science, but we're going to come at it from a totally different angle. So forget about cosmic lotteries, forget about miraculous one in a billion chances. Instead, we're going to explore the hard physical rules that might have made life, well, inevitable.
I mean, this is it, right? This is the fundamental puzzle. You start with a planet that's just a messy soup of simple chemicals. It's chaotic. And somehow, out of all that randomness, you get the incredibly intricate, beautifully ordered machinery of a living cell. How on earth does that happen?
The typical way we think about this is like winning some kind of cosmic Powerball. The number of ways atoms could possibly combine is so ridiculously huge, so mind-bogglingly vast, that forming the specific building blocks of life just seems impossible. Like you'd have a better chance of getting struck by lightning 1,000 times. It feels like a miracle. But this is where we flip the whole script. What if it's not about finding that one winning ticket among trillions and trillions of duds? What if instead it's more like a process of elimination? A system where almost all the tickets instantly catch fire and turn to dust, leaving only a tiny handful of viable options behind. And that brings us to the core idea here, the boundary conditions of matter. Just think of it as the universe's non-negotiable rulebook. It's the set of basic physical and chemical laws that straight up dictates what kind of stuff can exist and what just can't. And we're not talking about suggestions or probabilities here. These are the hard, unforgiving walls of a maze. If a molecule is designed in a way that can't exist within these constraints, it doesn't just struggle, it vanishes. Poof! Game over. So you can think of it like this. Any potential molecule trying to exist on early Earth had to get through 3 absolutely brutal tests. First, is it stable enough to not just immediately fall apart? Second, can it even form in the first place, or is the energy required to make it just too high? And third, do the atoms actually fit together without being so strained that they just break? And just look at that number. That second filter alone, the can it even form filter, wipes out 99.99999% of all the mathematical possibilities. That means almost every single molecule you could sketch out on paper never even gets a chance to be born. It's disqualified before the race even starts. This is where the rules start to act like a kind of chemical grammar. Like in language. Take valence, for example. Carbon always forms 4 bonds. Oxygen forms 2. That's the grammar. Most combinations of atoms are just chemical gibberish. They're like nonsense sentences that violate the grammar, so they just collapse. Physics is a very, very strict editor. Here's a perfect, concrete example of that geometric filter in action. Check out the stability of these rings. 4-membered rings, way too much strain. They just snap. 7-membered rings, they're all wobbly and unstable. But 5- and 6-membered rings, oh yeah, they thrive. They're the sweet spot. And it is no accident that the sugar in our RNA, ribose, is a nice, stable 5-carbon ring. It's not luck, it's just good geometry. Okay, so we've got the rulebook, we know the laws of the game. But where was this game actually being played? Well, the arena was early Earth itself, the ultimate crucible, and the final proving ground for every piece of matter. And this environment was unbelievably violent. Think of it like you're playing a game of Jenga, but the table is constantly and violently shaking. You've got intense radiation from the sun, endless lightning storms, extreme heat from volcanoes. There were 0 safe spaces. And remember, no protective enzymes like we have in our cells today. Only the toughest, most stable structures had any hope of surviving this chaos. And these forces, they were a real double-edged sword. Take UV radiation. On one hand, it was this relentless, destructive force just blasting molecules apart. But on the other hand, by breaking those bonds, it was also creating these highly reactive little pieces that could then form new, sometimes more complex structures. It was this constant cycle of creation and destruction that basically selected for anything tough enough to handle the energy. And get this, even water, the thing we think of as the source of life, was a relentless filter. It's the universal solvent, right? It's brilliant at pulling things apart. So any molecule that hydrolyzed, that just broke down too easily in water, it was just erased, wiped from existence. To survive, you had to be water compatible. It was totally non-negotiable. So, after running this absolutely brutal gauntlet of physical laws and environmental chaos, what's actually left standing? Who are the survivors of this incredibly unforgiving chemical maze?
Well, first, let's pour one out for the fallen. The vast, vast majority of structures failed. They dissolved in water, they got shattered by sunlight, they unraveled on their own, or they just couldn't even form in the first place. Survival was the profound exception, not the rule.
And so here are the survivors, and they should look pretty familiar. These are the building blocks of life. Ribose survived because its 5-carbon ring is geometrically rock solid. Fatty acids survived because in water, they automatically snap together to form these protective little spheres. You see, they didn't win a lottery. They simply endured the gauntlet. They weren't the lucky survivors. They were the only possible survivors, and they became the inevitable seeds of all biochemistry to come. And that leads us to the single biggest idea to take away from all of this. Given the fundamental laws of physics and given the harsh conditions of early Earth, the emergence of these specific molecules wasn't some freak accident. It was a predictable, almost inevitable outcome of how chemistry works.
So I'll just leave you with this question to chew on. What if life isn't a staggering billion-to-one coincidence? What if, instead, it's just a fundamental property of matter? Something written into the laws of the universe from the very beginning, just waiting for the right conditions to emerge.